Hi friends, in this video we'll discuss about the coal combustion which is been injected into the funnel and the air which has been moving out from bottom to top, as you can see on the screen. I'll just explain you using this paint. So now if you see from here, the coal will enter. So the coal will enter it from this point. So these are the coal particles you can see on the screen, and the air will enter from this side. So now the hot air, with when it comes with a cold particle, so the air will come into the cold particle. So there will be a devolatilizing species. Devolatilizing species means, so the species which turn into different fractions or which vaporizes. So one among them is H2O, which is attached to the coal, will now vaporize, and remaining like carbon dioxide or carbon monoxide, water in present in the coal, will try to evaporate from the coal surface. So these are the devolatilizing species that will be added into the devolatilized species that will come out from the coal. So this is the process, and for this to happen, it will need to reach the vaporization temperature. So if it reaches the vaporization temperature only, this will be vaporized, devolatilized, and after reaching the flash point, the coal starts combusting. So here the temperature of the air should be above the volatilizing and the flash point temperature, or else this cannot be evaporate and cannot be combusted. So the in this simulation we will try to check how the air will push these particles and also combust these particles. Now we can say this is like a fluidized bed reactor. So fluidized bed reactor means where the force that is coming from the bottom direction is able to push the particles in the top direction. Instead of getting the particles settled down at the bottom, the particles tries to move onto the top of the thing. So here, if it is the particle, so the gravity force, or mg, will now be balanced by the upward lift force that is being given by the air. So the air upward lift will be balanced by the gravity. Then we can see it is a fluidized bed reactor. But in the packed bed, the gravity will be dominating the upward lift force. So the bed will be completely packed and nothing will be floating, or nothing will be going in the top direction. So that is the difference between fluidized bed and packed bed. So now we are using the fluidized bed reactor only because the coal particles is small in size, and with respect to the air what we supply in the velocity, these coal particles will move in the top direction. As it is moving in the top direction, in the devolatilizing species, the carbon monoxide or carbon dioxide which are attached to the coal, they also starts evaporating when it reaches the vaporization temperature. So this is the domain what I have considered. You can see this is the outlet, and this is the inlet of the coal, and this is the inlet for the hot air. So first I will try to mesh it. So I'm trying to open the mesh. As it is an academic version, we'll have only 4 cores. So I have the graphics card, so I'm using 3 processors plus one graphic card interface. Then I'll try to import the geometry. So I'm using the watertight model. So go to watertight geometry, import geometry, browse for the geometry. So my geometry saved outside. 1 second. So here it is, geometry import. So we can add a local sizing if required, but I'm just leaving as it is. So update, and maybe I'll go to the side and I'll try to give size to scope, and I'll decrease the maximum sizing function to 3, apply, and the curvature to be 30, and this is the face onto which the entire object I want to apply the curvature angle. So create, so compute, and after that maybe I can give proximity also. So delete size field, and I'll try to give a proximity function also to the entire body. So 3 cells per gap, and can create, compute. Then we need to go to geometry objects, and this right click as remesh. Of course, there's only one geometry, you need not worry about these options. So now it is meshed. Now we can go to the connectivity and check for what is the quality of this. So we can go to console and check the quality is bit worst. So we need to use these options in order to improve the quality. So we'll just check if there are any point contacts around all this stuff. So if nothing is present, then you can just smooth these things, and we can just try to improve the geometry quality. And so there are so many spikes, I think so. Yes, there are some spikes in this geometry, so it was showing some problems. Actually, this kind of simple geometries should not have any problems. 56. I'll smooth all those things. So now our thing is closed. So now we'll check for intersections. Everything is resolved. Now you can go to the volumetric regions, compute it. So after computing, we'll have it a simple geometry. Change stage to this is a fluid, and in this fluid we need to define inlet, outlet, and all the stuff. So this is outlet, pressure outlet. So this is just an outlet, we can say. And when you go here, so this is the coal inlet. Select this, name it as a coal inlet. So 1 second, we'll take mass flow inlet maybe. Next, this is air inlet. Okay, now we'll go to cell zone conditions, auto mesh. In this auto mesh, we'll try to give, okay, we'll try to select all these things as a wall condition. So this is a wall. We'll mention here it is a wall. So this is a wall. Okay, so now we'll go to auto mesh, and in the scope we'll try to select selected labels, and we'll give this, I think it is not taken as the walls, maybe we'll define this. So we need to compute this, sorry, so we'll compute this. Again, change type, fluid, auto mesh. Okay, we'll select this on the walls. So on the walls it will try to create uh, the inflation layers, and we'll try to get a poly, this one. So everything will be happening here. So now we got the quality. We'll just improve the quality what we got. Auto node move, select all the things. Diagonal angle of 3, iterations 5, quality measure inverse orthogonal quality, and apply. So there are no cells above that quality, so it's a good one. Now we'll switch to solution mode. So I'm switching to solution mode. So you can run transient simulation. Transient simulation is much more accurate, but for time being and for time constraints, I'm using running a steady state simulation. Steady state simulation cannot be a steady state, but I'm using a pseudo transient approach where it will try to mimic the steady state. So actually, it shows it will take its own time step for running the solution, whereas in transient we'll give the explicitly the time step. But if you give a pseudo transient, it will try to take implicit time step depending on the conditions, and further it will try to have a converged solution. So first we need to go to species, and on the species with volumetric on and finite rate dissipation model, coal calculator, and we are using only one step reaction where the coal is being converted. So apply, okay. You can neglect this warning, it's not an issue. So then let's click on OK, and in the materials now you go to mixture, coal voltages here. So you can see here, these are all the species what they will react. right? This is a solid what will react with the species, and these are the outputs of what you get. So this is the Arrhenius rate, Arrhenius constant, and pre-exponential factors on which the entire reaction will depend upon, right? And the mechanism, density, these things have been taken by default. Now you can go to uh, we need to add air also into this, uh, or maybe we can take oxygen as a species for this in order to have this. So we'll take that combination, not an issue. Then go to cell zone conditions, and sorry, we go to discrete phase. We'll need to create an injection for this. Try to create a new injection. The new injection, combustion. So where the coal particle evaporating species is H2O, devolatilizing species which comes out of that is the VOL, that is the devolatilizing species, from which all these evaporating species will ejected out. And so the position and all these things it is asking. We'll try to give the surface, and that surface is the coal inlet, from which we'll have an x velocity, maybe positive. We can scale this up to phase area. So depending on the amount of phase area available, the number of particles will be adjusted according to the ratio of the areas, and in that normal direction. And I'm taking the particle as this. It is like 10, sorry, um, yes, it's 10 microns what I'm considering here. And the temperature is 300. Velocity magnitude I'll take 0.01, and this is 0.001 kg per second. And okay, so now these are the injections that will happen. Now you can go to the boundary conditions. In the inlet, we can go the air inlet, which is a mass flow inlet for the air, and I'm taking it as normal to the boundary. And mass flow rate of air I'll take 0.01 kg per second, and the temperature will be like 500 because we need to be above the devolatilizing or vaporization temperature, and the flash point 600 I'll take. And the species is oxygen, I'm taking 0.23, and the CO2 is 0.1, right? And water vapor is nothing, and the remaining is oxygen, nitrogen, that is by default is considering. And DPM it should be SK. Okay, so apply, close. And in the coal side there is no mass flow rate for air, so we can take the species for the coal side. These the fractions, these are already given in the DPM, so we need not worry about these things, because anyways this will be zero mass flow rate. So we'll take normal to the boundary, and the species you can take 0.23 and 0.1, but it will not bother because here there is no velocity given to the flow. And the outlet is pressure outlet what we have considered. So now exactly what we have stated will happen, which is the particles will be injected, and it will start devolatilizing species or anything which need to be evaporated with respect to the volatilizing species. It will evaporate, and the remaining will start combustion. And after combustion, the byproducts are carbon dioxide, water vapor, and all the remaining stuff. So now we'll try to initialize. So initialize, and after initialization we can just go to run calculation. And of course we'll go to methods, and we'll place it as the first order. Second order it will be difficult for the convergence. After running few iterations we can turn this into second order again for the convergence purpose. So pressure will take a quick scheme. And yes, now we'll try to run using the pseudo transient approach. So this is pseudo transient approach, and I'll just show you what is the vaporization temperature for the coal what we are trying to combust. Is vaporization temperature is 400, and as we have given 500, so automatically it will start evaporating. So 500, I'll give 500 iterations. This does not converge, but it is mimicking a pseudo transient approach using pseudo transient method with unknown time step. The time step will be taken by the system itself. So we'll try to calculate. So I've ran for a few iterations, so you can just check. So this is the temperature how it is been. Initially it is at 300, but as air is coming in contact with that, the temperature is raising. the air is nearer to this point, so the temperature is around 450 and it's going above, and these circulations are due to the air injections. That is the reason. Maybe we can have a vector of having a section along a plane, maybe in along the xy plane. You can just check. Okay, so I'm sorry, plane, xy plane, create, can just select that and check for velocity. So this is the velocity which is presented here. So there is a huge velocity differences at walls. You can just clearly see that. So that is the reason why we are getting a swirling near the walls. You can see the swirl near the walls. It is evident because there is a huge velocities near the walls, maybe due to that a drop in pressure. So you can just check. I'll just show you the other way on the plane along the yz. Just create. So now you can see both planes. Yeah, so there is this negative or low velocities, and here there is high velocity. So this is pushing on to that side. So that is the reason why there is a swirling near that. And we will see the other properties of the particles also. Particle variables, maybe we can go for particle positions. Oh, the positions are getting varied. Of course, this is why it is high position. That's the reason why it is in red color. And we'll try to check the swirl velocity. Yes, so it is having a swirl velocity here and it is going there. And this is at an instance of time, so it will vary. And particle variables, we can just check for particle diameter. We have given one diameter. This diameter reduced. Yes, diameter has changed compared to the particle dia. What you have given, the particle dia has been changed. And particle Reynolds number. Particle Reynolds number is also getting changed. Initially, with respect to the velocity and flow rate, what you have given, it has been changed. Yeah, so I think hope this video helped you guys in understanding how the combustion of the coal takes place, and how what is meant by fluidized bed reactor, and the DPM, how the DPM, how the discrete phase modeling is turning into Eulerian by conversion from fluid or sorry solid coal to the combusted evaporating species of volatile VOL and everything. So please do subscribe the video and encourage me in doing more number of videos. For any other queries, please you can contact me. Thank you.